Is it working? Oh, it's working. Okay, let's see if there's a filter on it. Oh, I pushed the wrong thing. There is two filters on it. So that probably is perfect. Okay. That's weird. What this green edge is all about. Let's see if I do that. Okay, I don't know what the edge is all about, but it is what it is. So, okay, so this, I mean, this is just basically uh, trusses, and there's two ways to do them. And the book spends a little extra time, but what I'll do is I'll just come up with a simple one and show you the two ways at one time so that we just get to the point. I think now I'm in the, well, that's probably good enough. So in a truss, it'll sit there and it'll be pinned kind of to the ground. And these are all pin joints. So in other words, if you take a rod like that and drill a hole in it and then connect it to its neighbor like this, if you push this way, this little member will just swing down. It'll just basically swing down back and forth. So if gravity were pulling it down, this thing would just swing down and sort of do like that, and basically, so there's no moment against it. In other words, you're not taking this member and welding it there. It's basically not welded, it's just pinned. So that's kind of the restriction of this, and they do talk about it, that they don't accentuate the difference in my mind enough, but that's okay. So let's take a simple truss that sits like this. We have a pin here, and I'll just do the simplest version I can. Okay, so then I'll say I have a pin. Maybe I should just have the pin go straight vertical there. Okay. Here's a pin. So I'm not a great drawer, but there's a pin right there. Then it's up here. There's a pin right here. Now that's enough, but if I left it alone, it would just swing down like that. So I got to support it somehow. To make the thing as simple as possible on the first one, I'm just going to pin it like this and have these little rollers here, so that if the thing shrinks or grows, this point can go back to the left or right. And so now we got to know some lengths. So I'm going to make it simple. I'm going to say this is 1 foot, this is 1 foot. And if this is 45 degrees, that's going to be square root of 2 feet long there from here to here. And then, I don't know, it doesn't look like it, but I'm going to say it's still 1 foot from here to here. It's maybe a little bit longer than that visually, but it's okay. And then I'm going to say that this is 45 degrees too. And so I'll have to go back and put those 45 degrees again, and I'll say that's square root of 2. Now, at this particular point, nothing's happening because nobody's putting any loads on it. And so what you really need to have happen is somebody like put a weight of like, just say 100 pounds, just because. Now, the two methods, okay, depending on the book you look at, our book has the method of joints. I have seen it also called the method of pin. less likely than it being called that, but I have seen that in another book somewhere. So we'll start there, and then there's another method called the method of sections, and we'll do both of those. But first, we'll do the method of joints first, and then we'll do the sections. And the thing is both these should come up with the same answer. So what you do with the method of joints, which is the one I was going to do first, is we'll make the pen a little thicker like that. That's a little too thick. Go to there. There we go. So what we'll do is we'll focus on each of the joints. Usually there's a number or a name for them. Sometimes they're not. I'll just call that joint A. I'll call this one joint B. I'll call this one joint C. And I'll call that one joint D. Now, there's kind of something interesting here. Almost all the problems initially talked about are 2D. There is 3D, but we'll delay that till we get done with everything, and then we'll do 3D. But in 2D, you got sum of the forces in the X equals 0, and the sum of the forces, in the Y. Actually, I'm not sure I like this pen. I think I'll go back to a different color or something. And you get two equations. So this kind of means you have two unknowns. Now, you can solve as many as two unknowns. Now, there is some of the moments, but when you're talking about a point, and that's kind of why I think that one book uses the method of pins. If you're looking at a particular point in space, and you've got these forces all on it, then all these forces pass through that pin, and there is no moment. So there's no moment equation for that reason. So what you're looking for is you're looking for a situation in which you have two unknowns that you can track down. Here's what I mean. The eventual goal is to find the force in this member. I'll just say FAC because there's a C on one end and an A on the other. And then this one will be called FAB because there's an A on one end and B on the other. And this one will be called FBD for obvious reason. FDC, and I don't want to forget FBC. So I've got a bunch of these forces, and at this point, none of them are known. But if I look at this pin right here, I don't know this one, I don't know that one, and I don't know that one. So I don't know three of them. There are three unknowns there. If I look here, I don't know this one, or this one, or this one. So this one has three unknowns. Now, actually, this one's kind of a misnomer because I don't know the support load. I don't know the support load Y. I don't know that. I don't know that. So this one actually has four unknowns at the moment. And this is the only one that doesn't have or can be solved. It has the load here and the load here, and that makes it two unknowns. So if I go in here and get rid of all this now, go back to this thing, that's the one I have to start at because it has two unknowns. And then as we go through this, I'll track down where we go next. And so let's sort of look at the free body diagram. And so what I'm going to do is copy A, and I'm just going to pick, and let me go ahead and take a minute and draw the expanded view, the complete free body view here. And so I'll try my best here. So I'll call this AB, and then what I'm going to do is I'm going to say I'm loading it here, and I'm pulling the pin apart here at A because that's where that pin is, and then I've got a load here and a load here. And so what I'll do is slowly construct this thing. So I'm pulling the members away and putting their loads here. Okay, this is A, C. So this one is this member. And this one right here is that number. And so as I'm doing these, I need to go ahead now, and you'll see I'll keep building this little tree in a minute. I guess you could call it a tree. Anyway, here is FAC, but equal and opposite FAC right here. But you know what? I kind of want to move this FAC over a little bit. Maybe I should do it this way. I should just put in between here FAC. So the force AC is this one, and it's that one, because I've split them apart. And this is just the pin by itself, or the joint, or whatever you want to call it. And here is FAB, but it's the same thing on the other end. FAC and FAB. So we'll see in a minute that I'll put a pin right here and call that pin B. And then I'll have the forces here, here, and here. And I'll go ahead and fill those in a minute, but I'm going to focus on A for the moment, and we'll fill in all those in a minute. So as I zoom in on A, there is one force that I've left off, and that's the weight. Otherwise, if I didn't have that weight, the problem would be pretty boring. There wouldn't be really anything there. And so I've got that. I've got 100 here. Now, I'll do, through the magic of this weird pen, if I can get it to work, I'll do this. Oh, how do I do that? I don't have my keyboard attached here. I forgot to bring my extra keyboard. So I'll do a copy, come over here, and do a paste. And I'll focus in specifically on it as a problem. And that's why I'm pulling it off to the side. I don't want to confuse the diagram by putting too much information right there. And so now I'm just focused on sum of the forces in the X equals 0. And so what I get is I get, okay, now we have to remember, I think I made everything 45 degrees. Okay, so, and I did that just to make things simpler. So this is 45 degrees. And this is going to be 45 degrees. And I'm just doing it to make it simple for the moment. It can be anything there, you want. So this means if I zoom back in on this, and you got 45 degrees there, then if I've drawn this the way I'm going to solve it, then there may be a minus sign that shows up. And I'm going to just do it because this is what I've drawn first, and then I might flip the vectors in a second. So what I get is I'm going to say to the right is positive. So I've got this one, FAB, and then I've got this one, but this one can be broken into components, basically the X component and the Y component, and this is FAC. And so if you do that, you're looking at this component, it's basically FAC, and it just happened to be square root of 2. The reason being is that this is 45 degrees, and this is 45 degrees too. So FAC times cosine of 45 is the same thing as FAC sine of 45, which is equal to FAC over square root of 2. That's all it is. So I'm sitting here looking at that. Let me check something real quick. I'm sitting here looking at that, and I have an interesting we're sitting there looking at this thing, and I got 2 minus signs. So something's going to give. One of the forces is going to have to flip. I'll worry about that in a minute, which one I'm going to flip, but I simply have one of the equations right there, and that's all I got. I don't want to adjust it quite yet. But first thing that, Okay, the next thing I need to do is sum of the forces in the y, and I'll make that one be positive just because out of habit. My habit is that this is, I like the coordinate system like that, plus no, and I like that. So I always choose that and that to kind of fit that. That's just me. Okay, so this one has no y component. So I take that back. It has all the y component. Minus 100. I basically said that backwards. And then I have a y component coming out of here that's sitting right here. Now, it's going down as well, and it's FAC over square root of 2. So immediately with this one, you see up that something's up. Okay, so we look at this and you say, okay, well, FAC. Okay, so I don't know which one you want to do. I could take this one and move to the other side or the other one. But in either case, I'm going to end up with minus. I don't know whether to put the square root of 2 first or the 100. So I'll do that. But the key is suddenly I realize, oops, backwards. Backwards assumed direction for FAC. I got two choices. One, I could just leave that. Or the other is I could say, you know what? Since I really didn't goof up too bad and I can constrain it right now, I can go back in and do something really weird. Now, when I got these pins, I can mess with things. And so that's what I'm going to do. I'm going to go in here. Go away. All right. And I'm going to go ahead and flip the thing. I'm going to say, well, it has to go this way. If that's the case, everywhere I see FAC, I'm going to put a plus sign. And then this is going to become plus. So I'm sort of correcting it. If I'm correcting it, I got to, here, let me go in here and correct it here. I think if I did that, I'm doing this, doing that, doing that. So I'm correcting the direction now. Now, some people will choose to leave it. This is kind of a personal preference. So now it's not a backwards assumed direction. And I get a plus value. And then I can take this and put back in here. And if I've got FAC, let me rewrite this equation out. 0 is equal to minus. Well, maybe I can move the FAB already over. I'll say FAB is equal to. So if I move this one to the other side, then I get that. And then I get FAC over square root of 2. But FAC is this. So I just go ahead and replace it. Square root of 2 times 100. So FAB is equal to 100. So suddenly I got two of my numbers, two of my internal loads. One's 100, and then the other is square root of 2 times 100. But I have to go back to my drawing here, and I realized I flipped this thing. So now I got to go back over here and say, well, you know what? It's supposed to be like this. And so this is supposed to be, this is supposed to be like that, equal and opposite. And that means this one has to go like that. Now, it turns out this one is 100. And this one is square root of 2 times 100, whatever that number is. 77, I think, or something. Or maybe just 70. I don't know. It doesn't really matter. I mean, I'm just going to use the square root of 2 right now. No, wait. Square root of 2 is 1.44. So it's 140 something. It's 1 over square root of 2. That's the 0.7. So suddenly now, I got that. And guess what happens? That's 100. If that's 100, then guess what? That's 100. And if this is square root of 2 times 100, so's that one. And so suddenly, let's look at pin B for a second. Pin B, now I know this one. I don't know that one, and I don't know this one. So I could work off of pin B, or let me go ahead and draw the pin directly under it. So if I look, here's B. I'll kind of draw, this is not, so here's point C. It's kind of gotten spread out of control. This is, here, I'll tell you what, let me do this. I think if I'm careful, you just move this down there. Oops, okay. So these are the two vectors here. They're actually, FAC is equal to that. C, I wanted to be directly under this B, so I don't know if I accomplished that, but yeah, one of the nice features, I can sort of move that, and now I did accomplish that. Okay, so now this is BC, so this will be FBC. If I'm assuming it that way, this is FBC as well. These are both equal and opposite. And then I've got this member right here. It's going to be over here to the left. And it's going to be called DC. FDC, okay. I'm going to make it go that way. FDC. And if it's doing that, it's got to go FDC over here. And then somewhere right around here. Look at that. I almost lined it up right there. That's luck. That was pure luck right there. So this FDC is kind of right there. And this FDC, whoops, kind of right there. Oops. I got that goofed up a little bit. Yeah. Okay, FDC. Okay, so since I did this, I might as well do that last member right here. Okay, so here's this one. And it comes down here. And this. And then this one. Now, there's something interesting about both this point and that point. And I should have dealt with those to start with, but I did not. And so what I'm going to do right now is go ahead and put that there's a support member here at C. Let me move the C over. And this is going to be CY. And I'll say support force. Now, what I'll do is I'll deal with that in a second. This will be, what was this one called? A? No, this one was called D. So this is point D. So here is dy, and this time it's able to take a dx. Now, that one is point B, so this is FBD. This is FBD. Now, my drawing isn't as nice as like the ones you have in the book, but that's essentially what it is. You've got members that you split away from your pins, and what you're doing throughout these is you're working on your pin. So we worked on that pin already, and then we go through here and work on all these other pins. However, I should have done this, and let me rewind a second and say there is before you start working on your pin, you can do another thing here, and that's this. And what I'll do is use the magic here that this provides me, and then I'll do C for copy, and I'll move way over to the right, maybe right here. And I'll do a paste. Oops. Hopefully it stays together. And what I'm going to do is take a minute to work on this. And let me show you what you can do to work on this. Uh-oh, how do I do that? Okay. So one of the things I can do is I can recognize what each of these supports have. So in other words, I can go in, I can remove the support, and I can say that, uh-oh, I have that, it gets stuck like that, so I have to hit the escape key. Hit the escape key, and pull that back off. I'll bring my other keyboard next time. And so this support can only supply a force upwards, and it's CY. And that's the CY that we put right in here. That's your support force. But this one over here, and I'm going to probably have to redraw the thing, because if I get rid of these, yeah, it's going to look really ugly. So I'm going to try to make it look a little better. And then I'll go in and put the support forces there. That'll be a DY. And this will be a DX. So I got 3 support forces here. This one, and this one. And those can actually be determined right now. So the way I can do those is look at the entire structure as just a rigid structure. And I can do something really strange, like sum the moments about point C equaling to 0. Now I'm doing this as if this entire structure is just a solid chunk. So it's just now, in my mind, it's a big solid yellow painted piece of steel or aluminum that has this shape, and that's it. So as I go in there, I'll sum the moments. I'm going to assume that direction is positive. I have 100 pounds going like this around C, and so I think that's a minus 100 times a moment arm of 1. That's 100 times 1. And I guess I really should put the 1. Now, this force goes directly through C, so it doesn't produce a moment. And then this one doesn't go through C, but it produces, in the way I assumed it, it's producing a moment this way. So it's going in a negative direction as well. So you can pretty much see it's 1 unit of length over. The drawing is not really to scale. And it's dy. So dy is equal to minus 100. Oops. Minus means I assumed it the wrong way. So I can, if I so desire, turn around and do like that. And then if I do like that, then I get this. That makes sense, because if you look at it, what you've got is essentially a steel or aluminum object or wood or something that looks kind of like this. It has a support, a force here, CY. Now it has a DY, and it has a DX, and it has 100 pound this way. So essentially, these are the loads that are applied externally to this object. Just so happens this object is the truss system. So this is I'm not a great drawer, but this is the object. This is that object right there. And so we actually found this. It's 100 units, 100 pounds, whatever you want to call it. Now maybe I want to find this one. It kind of makes sense. I would want to find that one next. So I will sum the moments about point D, this point here, or if you'd rather see it back here, I'm going to sum the moments about D. What you're going to end up, of course, you have to assume what's positive. And so about D, I get this producing a moment going this way, which actually, believe it or not, that's positive. So that'll be plus CY times the distance from here to here, which on the drawing was 1. There's 1. And now I'm summing the moments about this point, and I'm going straight across all the way to here because that's the 100 pounds. It is actually going the other way, which is minus 100. But its moment arm is not just this one, but this one added together to give me a 2. And so CY, okay, so if I move the CY over, it becomes negative, leaves the other one, so it's two. Did I say that right? 2, yeah, 200. I don't know why. Anyway, what do you think dx is? Okay, so if I just look at this object, here, let me erase all the external things and say I just have an object in space. Looks like that. Any idea what dx would look like there? Just from observation. So this will go down, that'll go up, this will go down. Nobody's there to offset that. So if I do a sum of the forces, that's going to just give me a 0. So in essence, let me see if I can write those values on this drawing and possibly transfer them back over to my breakdown. And really what I should do is I now should box these things. That was my pin for A. Now I'm doing the overall up here. Oh, I get more. Huh. Okay, I did not know that. Wonder if I can move this to the right. I cannot move it to the right. Okay, that's okay. So I get this. I get a value here equaling to 0, a value here equaling to 100, and a value here equaling to 200. So now I can go back to my split diagram, so to speak, and I can look at my support force. That was equal to, I think that was 200. Let me double check. Yeah, the CY was 200. Okay. This one right here, this one I think was 100. Yeah, I think that was 100. This one was nothing. So, in essence, if I do this external support, I could have actually done this one because then I would know this, I would know that, I would not know this one, and I wouldn't know that one. So I could actually have done this one first if I wanted to, but it's you know, there are many times you'll see multiple places you can start. But what you're doing with these method of pins is you're solving one. So we did this one first. At this point, I could do this one next, or I could do this one next. I could do this one next because I don't know this one and I don't know that. Um, leaves me with two unknowns. I could do this one next because I don't know this one and I don't know that one, but I know all the others. So I could do any particular one next. I don't know which one's the best to do. So in essence, I'm just going to take one. I'm just going to take this one. I'm going to do a copy, and that's my pen. And I'll do a copy. I'll drop down here to say right about here maybe. And I'll just take off and start solving it. And maybe I'll move it up a little bit so that I can have a little space right here. Okay, so here you go. This is a first thing I see is I'm gonna have a problem with my assumed direction here, but it's okay. I can go back to the main drawing and flip it after I do this. So I'll go in, I'll do sum of the forces in, say, the x direction. Remember, everything is 45 degrees. I did not write those values down, okay? Well, I did. I just didn't copy them. BD, okay, this is FBD, and this is FB something, BC. So there's FBC. So in this, what I'll do is take the FBD and break it into a component this way and component that way. Turns out that that's FBD over square root of 2 for both of these components. So I'll assume that's going to be right. I'll know this is already 100. And then what I'll do, I'll take that one, which is FBD over square root of 2. And so FBD is equal to, I'll do the square root of 2 first, times 100. That's okay, because this component has nothing in the y direction, so it doesn't even show up in this equation. And so we're okay. We got that one. I could go back to the main drawing and put that in there. Okay, so wait a minute. 100 times square root of 2. So this is going to be 100 square root of 2. And that's going to be the same thing down here. And we got it. So we got this one. We got the load in that one. We got the load in this one. Now we got the load in that one. We're about to go after this one next. But we're going to find something interesting about the assumed direction. So we go in here. We sum the forces in the y equals 0. I'll make that positive. So this is negative and that's negative. That's going to represent itself as a problem. So negative. And what we're doing is, here, let's see if I can move this out from in here. So I'm taking FBD, which I actually found it's that. Okay, so I'm going to write it down as that. So it sounds weird, but FBD over square root of 2. This component going down becomes minus, which is why that is. And then I get this one going down, minus FBC. Now what I'll do is I'll take this one and stick in here. And then I'll say 0 is equal to 100 times square root of 2 over square root of 2. And it's still a minus FBC. So that cancels, that cancels. And then you move that over and you get FBC equals to minus 100. Uh-oh, wrong direction assumption. So now I can say, oops, I'll use my special red And I'll say, whoops, I will go back and I'll make that one go that way. If it goes that way, then this becomes positive. If that becomes positive, then so does that. And suddenly I realize I've assumed this direction and that have to line up. So I have assumed the wrong direction here in this one. So I'll fix it. That, oops, that, and that. And I think it was 100, right? Yeah, it's 100. So suddenly I know that one. So we started here. We did that first. And I think we just finished this one. So I don't know which one to do next. I mean, we'll just do this one next. Might as well. At this point, I know everything except that one. So it should be fairly straightforward. So here, I'm going to just try this time to copy as much. Oh, shoot. Okay, try it again. If your finger slips off that thing. Oh, it slipped again. Okay, well, I use this, so I don't have to hold it that way. Oh, wait a minute. Yeah, I wanted that. I wanted this. And I wanted that. Okay. Now, I will bring my other keyboard next time. I'll put it right here. There it is. Okay, at the same time, I'm going to subdivide this because this was node B, this was node A, and what I'm about to do here is node C, and I don't know how much space I'll need, so I'll just do that. I don't think I need a whole lot of space. And ironically, don't know that I need a second equation, but you know what? This is a good time to do a check. Okay, so let's do a check. This is a good way to check yourself. Okay, sum of the forces in the y. Okay, I don't like that here. Sum of the forces in the y. I'll make that do positive. So first of all, I get the 200 there. Then I get the 100 going the other way. Wait, what happened to my 200? Did I erase it? I guess I did. Minus 100. Okay, got this right here. I got this one, and it's at 45 degrees. So I'm going to pull it over to the side. So it goes like that. It's 100 over square root of 2. So believe it or not, I get 100 over times square root of 2 over square root of 2 means I get 100 going down. And so this is nothing more than a check. It's like, okay, that I feel comfortable now because this one, and this one all add up in the y direction so that they're static. It's a check, so to speak. Then I'll come in here and I'll say sum of the force in the x. I'll make it go to the right, that. And then this is the one I don't know. And of course, you could probably guess what it's going to be. It's going to be 100 pounds. But anyway, we don't know that yet. So all I get is FDC. So I get this, and then I get the offsetting component going that way. And, you know, if I get this one, it turns out that this one's also 100 square root of 2 over square root of 2. So it's going back to the left at 100 pounds. And so what you get is FDC is equal to 100 pounds. And so you're like, yeah, this is good. So you go in, we'll say, okay, this was C. This was node C, which gave me this. And actually, I think I'm done, but I do have one I can check. So this is 100, and this is 100. So it is true, I got everything, but I should be able to check this one. I should be able to do D for just a check because I already have everything there. All the forces are there, but I should do a check just for the sake of completeness now. So I'm going to do a check. So let's see, I think I'm going to do I think I'm going to gather more things this time. Actually, no, let's do this. Let's get rid of that. And now I'm going to gather this. Okay. So now, oh, we're running late, aren't we? And then I'll go down here and put it right there, I guess, or somehow put it right there, or uh-oh, I gotta hit the escape and put it right there. But what you'll find out is this will check out okay. So maybe I'll just say we're good, and because I didn't realize it's 5 TL. So what you find out, so this is the method. So obviously I wasn't able to get the section, and that's with a small problem. So these can try your patience because they're long. They're not heavily intensive, like, oh my God, I don't understand or something like that. But it's more like, oh gosh, I got to do, how many pins do I got? This I got 1, 2, 3, 4. I got 4 here. If you look in the book, sometimes they'll have 8, 9, or 10 pins. And that's why the method of sections is so good, because you don't have to do them all. And I'll show you next time. You just take a dividing line and you just slice it into 2, and you can find them right in the middle right off. And that really shortens the amount of analysis you got to do. Plus, the thing about the method of sections is if you sit back and stare at it, you can get away with summing the moments and just having like one equation with the unknown in there, and that's it. And so this one, you can end up with just over and over and over, and it just gets tedious. But the other one is so easy to do for me that I like doing it a little bit better. So, so there it is in a nutshell. But that's not everything because I didn't get to the section. But we'll do that Friday. I'm sort of losing track of time because I've been out so long. So did that make sense? Did everything seem to be okay? Okay. What's that? Right. Okay, so here's the reason being. Okay, so if you look at this support, yeah, the roller, it can't resist movement in C in the left or right. So the C can just move to the left and right. So there's nothing to hold it. Does that make sense? If you did have 2 things, guess what? You wouldn't be able to determine the loads on either one. It's so weird. You can make an assumption, but that might not be correct. So yeah, does that make sense? And that's why you only have that vertical support. And I should have, in retrospect, I should have done that first. I should have done this part first to find those reactions. I just saw that and started doing pin A without even thinking. But the key is it didn't hurt the problem numbers. I mean, you can do that. As a matter of fact, if somebody just asked you for that load, they're saying, I really am concerned about that load, then you would never have to find the supports. You don't need to know the support. So there's often little shortcuts and things in these that are that vary a lot from problem to problem. So Do you think it would be helpful to have this printout, or now I don't know how to produce it, but I'm sure I can turn this to a PDF somehow. It's a lot of junk on the page. Yeah, yeah, that's true. It is, I do kind of freeform it a lot, so uh, maybe maybe that's what, maybe that's my fault, but at the same time, you know, anyway, I guess we'll see you Friday. And this week, I'm just going to give you like one problem because I've been out of sorts and I don't want to give you five or six. I'm just going to give everybody, I'm doing it for every class. I'm just going to pick the most relevant problem and just pick one and just do that. And then next week, we'll go back to two or three problems. In the meantime, stay away from that flu. That's my advice. That is not something you want. Matter of fact, several people that I knew had both this and COVID that said this flu was much worse. So, um, I mean, I don't really know, but I was out just completely oblivious for 3 solid days. So I didn't even know who I was at one point. You know. Yeah, I was.
Man, that looked like a fever trip.
Yeah, I looked back at that and I was like, did I write that? And I was like, oh geez, what did I write? Me equals fever 103 or something like that.
I read it and I was like, I know he ain't having not writing emails like that.
Yeah. So I knew it. I mean, I was sitting there. I have it so that on my phone I've got everybody's email, so I can go over to a Google Doc, copy it, go back to the thing, and dump it in there. So it means it's really easy for me to write an email. So I'm like laying there writing an email like this, and I'm like, so for 2 days later, I looked at it and I'm like, oh my god. But hey, this is life.